Hi, good morning. I'm Andrea Renieblas from Ata Insight, and I welcome you to this webinar, which is part of the event Red Mate Storage America that will be based in Panama City the 29th and 30th of October. If you want to ask the speakers any questions, you can put them in the Q&A box, and they will solve them in the last 20 minutes. This session is being recorded, and in a few days, we will give you all the materials used. And now I'm going to present the first speaker, which is Carlos Fernández Ramos. So you can start with the presentation.
Okay, okay, I'm going to share my screen. Okay, do you see my screen?
Yes, we do.
Okay, let me just start by introducing myself. My name is Carlos Fernández. I'm working as a best project manager in ATA storage, and I'm expert also in best modeling and simulation. Ata Storage is Ata Storage is the sister, is the best and green hydrogen division of ATA Renewables, and is the sister company on ATA Insight, the people that are managing this webinar. ATA is an independent, ATA Renewable is an independent advisory and engineering company with more than 16 years of experience and extensive international experience. In particular, we provide advisory service from development state, ready to build, project execution, and project operation. In my case, as I said before, I'm working in ATA Storage, is the specialized division of BESS and green hydrogen of Ata Renewables. We have so many experience in the different steps of the battery and in BESS purchase process with different clients and with more than 6 gigawatts of experience around the world. Okay, today we would like to, the objective of this presentation is to give you advice about the complete BESS purchase process. I've divided the presentation into 4 parts. The methodology related to the different procurement structure considered the best value chain. Secondly, we are going to show you at a high level the technical specification advice considering the technology. Then we'll explain our methodology or a standard methodology to select the best integrator. And finally, some important technical terms necessary to be added in the elaboration of the contract. Okay, we are going to speak now about the first point. About here, you can see a table regarding the procurement structures. The first row shows the typical players in the manufacturing and commissioning of a battery plant. It's we are going to analyze each one of them now. And here in the first column shows the scope of supply that are well known probably for all of you: the cell manufacturing, module rack manufacturing, container manufacturer, auxiliary service integration, PCS, EMS, interconnection and civil work, and operation and maintenance. Okay, in this table, the cell pink shows the players that can supply a particular scope. And inside each cell, we can see if the player can supply the product with their own technology or not. Okay, then in the first column about best manufacturer, some of them has their own cell and other no. However, they integrate the other elements: the container, the module, and the auxiliary system. Some of them has their own cell. However, others get the cell from other manufacturers. Okay, about container integrators, it's usual that the main function are linked to integrate the container and to integrate the auxiliary system. Sometimes, yes, I think that we think that it is the main objectives. About PCS manufacturer, it's usual that use their own PCS to integrate the rest of the component from other manufacturers, but sometimes they have their own EMS and sometimes they do not, depending on the manufacturer. Okay, about software developer, it supplies the EMS. It is an essential part because the EMS ensures that the battery provides the market service being best profitable. It is an essential part and it is usually providing only the software developer. But as I said before, PCS manufacturer or now best integrated can has this element too. About best integrator, here we have so many different variants, depending on the origin of the company, with no property technology, and they integrate the system coming from other manufacturers. Other integration are all the PCS manufacturers. Some PCS manufacturers have working now also with their own cells, and it is depend the company. Also, some best integrators are starting now to do all the scope of the EPC company, but it is a particular case and it is depending on the project and depending on the company, obviously. Then regarding best integrators, we can see here the different combination and the different own or not technology depending on the particular company. Okay, about BOP supplier, they are going to supply the interconnection and civil work. And about the EPC company, they are going to supply all the scope regarding BESS. And in all the cases, in the majority of the cases, they are not owner of any of the element of the value chain. Okay. Here you can see other table with the different strategy. We can see here 3 different possibility results in the purchasing structure of the BESS system. In the first one, we can see an independent purchase. It is the less common structure. Why? Because here we have several players: battery, PCS, EMS, also the BOP. And it is the main disadvantages. It is focusing APP companies with best experience or an EPC capacity, or companies with the capacity to purchase their volumes. Here we are going to have the best margin reduction because we can buy from different manufacturers, but it's the less common structure using in the purchase procedure. Okay, here we can see the most common structure. It is all these 2 players, best integration plus BOP. The best integration will be in charge to integrate all these things, the battery, the PCS, the EMS, and the BOP. And the BOP news, sorry, only the element of the battery. And then here also we have other players that call BOP. Here we have also margin reduction because we are contracting into 2 different players. And the best advantage is that all the technology will be under the same contract because the best integrator will provide the performance warranty, one of the most critical parameters. Here the last option, the option 3, is that the EPC company do the full EPC of your project. It is depend on the project context. It is just one player is the most advantageous, but depend on the it is usually used when a company is doing their first project, or when you are starting in a new geography or in a complex location. Okay, about specification, it is essential to have a good understanding of the technology. Why? Because the most important thing here is to know what is your minimum usable power and energy at POI during the life of the project, according as the result of your business model. And why it is important to know very well all these parameters, because depend on your useful power and energy useful power you need at your point of connection, we need to oversight more or less. We are going to know what is necessary to oversight in the concrete in your particular case. We need to take into account the energy one-way discharge, the depth of discharge, the state of health, and the state of health is going to be different at year 0, year 1, and at the end of the life. It's going to be degradate, and we need to take this into account in order to give to you the real installed power and energy you need. Also in the energy part, we need to consider the energy one-way discharge. From the charge way, we need to consider the efficiency of the charge and also the state of charge, the maximum state of charge. In case that you need symmetrical charge and discharge at POI, it is we need to consider other parameters. In this case, the DUD at contact discharge and the state of charge maximum at constant nominal charge. Installed energy makes up the biggest part of the cost of the battery system. So it's really, really important to figure out exactly how much energy you actually need in your project. It is an essential part. Okay, here we can see the different warranties that it's usual to contract in a BESS project. In the first column, we can see the product warranty. It is a standard warranty covering the equipment defects. It's usually that the standard product warranty covers 2 to 3 years at the batteries and 5 years to the PCS. Depending on the project, it is recommendable to extend the battery using a product warranty extension. Also, in this warranty, it is related to the spare part procurement necessary. About performance warranty, it is associated with the degradation of the usable energy curve and the degradation of the round-trip efficiency curve. Here, the standard of the manufacturer give to you is from 2 to 3 years of warranty performance to the batteries. It is not applicable to the PCS. But it is strongly recommended to extend the performance warranty up to 20 years and up to 70% of your state of health. Why is it so important? Because the bankability and the profitability of the project is going to depend about the performance of your battery. And if this performance is not guaranteed, probably we can have a problem in the future. In this performance warranty, also we can see different points of the maintenance contract. And about the availability warranty, it is referred to the percentage of usage during which the battery is available. It is common for the integrator to require a contract for spare parts and maintenance to ensure this warranty. All these things that I explained here, it is the standard, the most standard way that we have seen, but all these things is subject to negotiation condition agreed with the integrator in the particular project and in the particular client. Okay, about best specific recommendation. Here it is important to request regarding performance warranty value to request us warranty values, capacity and RTA efficiency. It is appropriate to make correct specification to be sure that the sizing ensure the system can be operated at constant rate power. Also, the proper definition of POI and integrated scope is so important. The environmental condition here is so recommend to review because the rating curve is going to be linked with altitude, temperature, or DC voltage. Regarding performance RTE, to define operation condition and request the RTE curve at different temperature and power level is also important, and also that the auxiliary consumption must be considered in this efficiency, because sometimes some manufacturers don't include in the RTA, and it is so important to review. About warranty, we spoke before about the different kind of warranty. It is important to adapt, depending on your particular restriction and requirement, the warranty to your project. About safety, depending on the country, it is probably that you need to cover, for example, the different NFPA rules, or you need to request also the safety certificate. We need all these things in a document, in the different files, the warranty agreement, the performance curves. And about the schedule, is so important that the deadline is aligned with the completion of the work to avoid calendar degradation of the battery. It's important also to define the beginning of life. What is beginning of life depend on the manufacturer, because for some manufacturer, this is when the battery leaves the factory, and for other manufacturer, it start when the battery is commissioning. And it is so important to define, to consider the calendar degradation and also the responsibility. About transport, we recommend to use DDP because it covers all the duty and all the shipping and minimize the risk. Okay, about the selection, it's important that when we need to compare or evaluate our solution, it's important that we can just look at CAPEX. Why? Because CAPEX is only the cost of the installed energy system, but the battery is going to be degraded and perform differently over time, and depend on the manufacturer, the degradation and the operation and maintenance, the OPEX cost is going to be different. Then we consider that a better way to compare one solution with other solution is to use the LCOEs, the levelized cost of storage. LCOEs give you a clear picture of the cost of storing and using energy over the lifetime of the system, because it takes the CAPEX into account, the operation and maintenance costs into account, and the warranty costs into account, and also the discharge energy along the different years, consider the degradation and the efficiency. Okay, then at the last point, we are going to speak to the two different contracts we have here, the supply contract and the LTCA contract. The supply contract is regarding equipment supply, commissioning and spare part. Depend on the contract, some spare part is in the LTCA. Okay, here is so common to have the product and performance standard warranty, the CAPEX, the penalties for delay, the penalties for warranty no compliance, and the plan acceptance after performance test. Regarding LTCA contract, here it is include the maintenance service and spare part management, the performance warranty, the flexible performance warranty. It is so important if in the future the regulation change, for example, our battery participate in other market and our mode of operation of the battery chain. Also, the availability warranty is considered inside the LTCA contract. The OPEX, yearly payment with cancellation option, and penalty for performance and availability warranty no compliance. Also, the yearly performance test to know what is the state of health of our battery. Okay, what are the conclusion? The conclusion here is that it's so important to define the most suitable purchase structure for your buyer profile. We see three different structure, independent, with 2 players, or one player. Depending on your profile, it is important to choose one of them. It is essential to have a good knowledge of the technology, because the technical specification is important to define the correct solution. If we do not evaluate correctly the specification, the technical point, probably we are not going to optimize our sizing. During the selection, it's key to analyze the battery performance to choose the best solution in terms of CAPEX, OPEX, and performance, not only the CAPEX and not only the installed energy. It's important to see is these 3 points. For example, using the LCOEs that I explained before. And it is important to define correctly the structure of the contract as technical debit, that it is that fulfill the plant performance and availability. It is essential to define in the specification phase to avoid future issues. Thank you so much for all of you. Here is the contact of the head of data storage, my contact. And if you have any question, we can solve later in the Q&A session.
All right. Well, thank you so much, Carlos, for that presentation, that walkthrough. Hi, everyone. I'm Cristina Galan, the moderator of this webinar. I'm so sorry, but just 2 minutes before the start of the webinar, my computer decided to reboot. But now I'm here, I'm back, and I was able to see the full length of the presentation. So thank you, Carlos, for for that presentation. As he said, if you have any questions, you have the Q&A box. So feel free to write all the questions, any doubts that you have if you are connecting from Zoom. If you are connecting from YouTube, you also have a chat available. In the meantime, I see that people are in the Q&A introducing themselves. So we encourage everyone to do that so we get to know everyone and get to know their background. Also, we are seeing questions about the presentations and the webinar. The recording and the materials approved by the speakers will be sent in a couple of days to your email. If you have any issues, just contact us to check what the problem is. So without further ado, we're going to go all the way from Spain to the US with Jakir. Hi, Jakir. Good morning to you. How are you doing today?
Hey, Christina, doing good. Thanks for inviting me here.
Absolutely. Thank you so much for being here today. So we're going to move on next to the presentation of Jakir. Whenever you're ready, you can start putting your slides on so we can see that they work correctly.
Go ahead and share my screen. Let me know if you can see it.
I see it now. Perfect. You're all set.
All right. Okay. Hello, everyone. My name is Sheikh Jakir Hossain. I'm the co-founder and chief technology officer here at Storlytics. So at Storlytics, we provide energy storage software solutions and consulting services for energy storage projects. Our flagship product is our energy storage, Storlytics energy storage software, which provides very accurate estimation of battery degradation, loss estimations, all the performance characteristics needed for designing and optimizing a battery project. So with that, I'm really happy to be here and share my insights with you all through this presentation. So when you talk about choosing the right battery for a battery energy storage project, there are several questions that comes to mind, right? So first question, you start with how optimize the dispatch of the battery, right? So if you're in a market, you want to optimize your revenue, you want to come up with a strategy that basically makes sure you get the most bang for your buck, as well as make sure that your battery's performance are not negatively impacted as you dispatch these batteries. You also want to know that what the deployment strategy needs to be, right? So do you need to overbuild throughout your project life of 20 years or so, or you're going to do some initial minimal overbuild and then you're going to come back and add capacity through augmentations? So how that's going to look like for your project? What kind of battery technology is more suitable for you, right? So the industry is looking at exploring LDS technology, higher duration, 6 to 8 hours and all. So for your project in hand, is lithium still is the best solution, or look at some other alternate technology, and will that make sense? And then eventually the other question that flows around a lot is about the auxiliary estimation of the site, right? Because it varies with ambient temperature conditions for lithium as well as uses. So there is always question about how to accurately estimate those auxiliaries and how these auxiliaries needs to be sourced, right? Because there are different architecture in the marketplace where you feed these auxiliaries from a separate source sometimes it's fed from your batteries, and all that impacts your performance, your sizing, your overall round trip efficiency between the point of interconnects. So these are some of the questions we'll try to address today. So before going into all that, right? So what's common in all those questions? The main theme that is common in all these questions is all these questions depends on your battery performance characteristics, and mostly it depends on your state of health, the degradation. Like for lithium batteries, one of the biggest characteristics is that they degrade with time, right? So they have calendar aging. So even if you don't use them, they will degrade, and they have cycle aging. If you use them more, they will degrade more, right? So there are several parameters that impacts that degradation, and that eventually, basically controls like how much battery you need to install to begin with, and then how much batteries you need to come back and add to maintain your overall project capacity. So first part, I'm going to talk about some of those parameters that basically controls degradation. So first to start with is the throughput, right? Discharge throughput, that's the most common, well-known one. So the industry kind of standardized around 365 equivalent cycles. That's what most projects are built on, because early on, the owners didn't know how to best operate these batteries. But as the market is maturing, now we are seeing more and more use cases being introduced, and owners have better handle on how they plan to use these batteries, where we see now more than one cycle per day, so more than 365 cycles. We see less than 365 cycles as well. But that is a very important factor that impacts degradation. So basically, the more you use a battery, the more it degrades, right? So the chart here shows you 365 cycles versus like 50 cycles a year, right? So you can see 365 cycles, the blue one gives you much more degradation compared to a 50 cycles, which is the red one. But for lithium batteries, that's not the only criteria, right? So even though that's the most well-known one, that's not the only criteria that determines the degradation. There are important parameters like depth of discharge, right? So what is depth of discharge? So it's about how much you are cycling your battery at one go. So if you are going from 100% to 0%, completely depleting your battery, that's 100% depth of discharge. If you go from 60% to 40, that's 20% depth of discharge. So what you see here is a example. So the black one here is between 100 to 25% state of charge, right? So that's around 75% state of depth of discharge. And the orange one here is around 10% depth of discharge. So what you can see here, to reach 4,000 or around 4,500 cycles, for the black one, which has higher depth of discharge, the battery will degrade much more, and it is going to reach around 75%, between 75 to 80%, compared to the smaller one, which is the orange one. So 10% depth of discharge is going to degrade much less. So even though you are performing same number of cycles, just because how the depth of discharge is, that has a significant impact on the degradation rate. And in this particular example, you can see it can be as large as like 18%. So now the question is, what controls this depth of discharge, right? Obviously, that's being controlled by the applications or the use case that you plan to use this battery for, right? So participating in a frequency regulation ancillary services market is a lot different than participating in an energy arbitrage market. In all these different applications, uses the battery differently, and in terms impacts these underlying characteristics differently. So it's important to take these factors into account when you're upfront designing these projects. Then the other important parameter is the average state of charge, right? So for lithium batteries, the higher you hold the average state of charge, the more degradation is going to cause, right? So in this scenario, you can see the average state of charge around 75%. The green one degrades much more compared to the blue one, which is around 25%. So in this scenario, around year 10, you can see a delta around almost like an 8%. So we're not talking about small pennies here. So 8 to 10%, 15% differences because of these characteristics can be significant as you are building these projects. And then there are also parameters like C rates, right? So 0.5 C versus 0.25 C, 0.5 C, you're cycling the battery at higher C rates. That causes more degradation compared to a lower C rate. So a 2-hour battery is going to degrade more than a 4-hour battery. So now that we understand that these are some of the factors that is related to lithium battery characteristics that impact degradation, the next question obviously becomes how that relates to my use case and how it impacts my overall project planning, right? So for that, so next section, I picked an example and thanks, shout out to Modo Energy for making this data available. So these are a comparison that they have done for a couple of projects in the ERCOT market, right? So they looked at 2 projects, 10 megawatt, 10 megawatt hour. So basically 1-hour project, both same size, participated in the ERCOT market, but both were subscribing to different services. So the Faulkner battery here was subscribing to more on the contingency reserve services. And then the Sweeney project here was subscribing more on the regulation up, down, and energy arbitrage kind of market. So over the 2023, both projects made similar amount of money, which you can see here, 215K versus 225. But the Sweeney project ended up using their battery a lot more, right? So you see it's 1.6 cycles per day compared to the Faulkner, which was 0.5 cycles. So even though both were same size project, participating in the same market, depending on the use case and the strategy that they are performing, one were utilizing their battery a lot more or using their battery a lot more compared to the other. So even though they get the same revenue, on the battery degradation and state of health, the Sweeney will have a much more impact, right? So these projects' battery will degrade much faster. So that obviously means now either to maintain capacity, this project, they would have to oversize it more, or they would have to do more frequent augmentation. So that's where the point is that depending on how you plan to use this battery, there is a big impact on the cost side of the equation. Your revenue is same, but the cost can be significantly different because your battery degradation and performance is going to be significantly different depending on your use case. So then the next question is, okay, so we understand that, how do we quantify it? How do we quantify that based on this use case, what my battery degradation is going to be, what my performance is going to be, and how do I optimize it? How do I know to begin with that this approach is much better on the left than the right-hand project approach, right? So to do that, you need tools that can accurately predict degradation, predict performance, let you do a lot of what-if scenario and optimization upfront in the project well before you place an PO, right? And that's where the Storlytics software comes into the picture. So from now onwards, the results I'll show is from the software itself. So this is an example project I picked to walk you through the process, right? How to do that optimization, how to compare different scenarios. So this is a 100 megawatt, 4-hour project. So basically 400 megawatt hour. So that's the goal, right? The goal is to maintain 100 megawatt, 400 megawatt hour at the point of interconnect for 20 years. We're going to look at 2 scenarios, right? So first scenario is a composition of 5 use case, right? Mostly heavily, you can see the blue one, which is the energy arbitrage. So almost 80% of the time, first scenario, we're doing energy arbitrage, then a little bit of regulation up, down, and a spinning, non-spinning reserve. On the second scenario, we're not doing any energy arbitrage. We're going to focus more on regulation up and down, and then doing a little bit of spinning reserve, right? So what we're going to look at for how these 2 scenarios, the degradation estimation and performance varies, and how that impacts the overall bottom line, the cost side of the equation. So do that, to simulate that, first you need to get the point of interconnect profile, right? So for each scenario, you have to come up with a profile that is a composition of these different services. So that's what we have here, and that's what you input as an input to the Storlytics software as the point of interconnect profile. And then the software is going to do all the calculation based on your interconnection, the profile that you're inputting. So in this scenario, this is the regulation up, down, scenario 2 profile I'm showing, for example. So you would do that, you plug it into the software, it does all the calculation, and then eventually it is giving you the degradation estimates, right? So what you see here is scenario 1. Remember, scenario 1 was where we were performing more energy arbitrage, and energy arbitrage we know is a more deep discharge cycles, so more higher depth of discharge. So that basically means to maintain the capacity of 400 megawatt hour at POI with the on-way efficiency and losses, we had to maintain a little bit above 400 at the battery terminal. So that's like 440 or so. The scenario 1, you needed higher beginning of life capacity compared to scenario 2. So both projects meet the project requirement for 20 years. This is a 20 years overbuild we are looking at, no augmentation. And then for scenario 1, because the applications are such that it uses the batteries more with higher depth of discharge, it basically needed a higher beginning of life capacity compared to the scenario 2. So now, based on that, you can look at the complete picture, right? Your revenue is one side of the picture, but then you also have to take the impact of this into the cost side of equation, and then look at the overall benefit that you're going to get from the project and your cash flows and everything. So to put this into perspective, if we look at the overall cost comparison, so scenario 2 versus scenario 1, so you could see there are 4 components here, right? And this includes both CapEx and the OpEx, but not it doesn't have the tax and other incentives built into it. So this is mostly focused on the technology cost itself. So the 4 parts here you see is the blue one represents the CapEx of your DC block, right? And then the orange one here is your PCS and PCS transformer cost. The gray one here represents the cost of maintaining your performance guarantees for the 20-year. So that's what Carlos was talking about, performance guarantee, part of the LTSA. So that's your cost of your state of health guarantee maintenance. And the green one here is your energy loss, right? So your no battery system is perfect, 100% efficient. You charge it, you discharge it. There are some energy that gets lost, and those energy loss is part of your O&M cost. So that the green one represents that. So what we see here, because the beginning of life capacity was more for scenario 1, so the DC block capital cost was much more for scenario 1 compared to scenario 2, and which led to basically scenario 1 to be more expensive than scenario 2. To quantify that, scenario 2 here was 9% less expensive than scenario 1. So this is kind of the tool that you will need to do some upfront optimization to choose the best strategy for your projects as you're designing it before you do the procurement. So that answers that part of the question about like how to optimize the use case, how to decide how you plan to dispatch your batteries. Next part of the questions talks about is about what strategy should I take for my deployment? Should I do 20 years, 25 years overbuild like that I was showing, or should I do a mix of it, some minimal initial overbuild, and then I do some multiple augmentation cycle? So degradation is a critical parameter for that as well, right? Because when you need to add capacity, it really depends on how much your battery is degrading, and overall your round trip efficiencies and how much those are getting impacted. So in this scenario, some examples, just ran it for 25 years. On the left, you see the overbuild approach, and on the right, you see the augmentation. So on the overbuild approach, you initially build it. So it's a 400 megawatt hour needed to maintain, initially coming around 650 or so for 25 years. But then on the augmentation you don't need to overbuild it that much. So you're overbuilding around 460, 470 megawatt hour upfront, and then coming back and adding capacity in multiple rounds. So there are 4 augmentation cycles happening at around year 6, year 12, and year 20. So those are being done keeping in mind that you want to maintain 400 megawatt hour at point of interconnect, and also you want to make sure that your cost of your augmentation is minimized. So it's a two-pronged problem to an optimization problem. So for both this strategy to derive at which one is best for your project, both of them maintain the capacity, right? So basically both of them are meeting the minimum requirement from a technical perspective. So now the decision point is going to be based on the cost. So in this scenario here, you see the augmentation cost and the overbuild for the augmentation project, because you are deferring the cost of lithium, adding more capacity up front, and the lithium price is going down. So at later year, the lithium price is going to be less, which basically make sure that, or which basically turns into a lower TC block cost for augmentation. So for this project here, the overbuild is much more expensive, roughly around 25% or so than the augmentation case for a 25-year project life. And all these factors are based on, this is the end result, right? But the inputs to this is your degradation estimation, your losses, your auxiliary loss estimation, your round-trip efficiencies. All these technical parameters needs to be very accurately determined for you to be able to accurately deduce, make good informed decisions. And then eventually the question becomes, okay, once you do all that, you also want to know what's the best technology for your project, right? So in this scenario here, you're looking at a non-lithium technology and comparing it against lithium with augmentation, specifically the LFP chemistry here. So the non-lithium here, you see the technical characteristics. It has much better degradation performance. So basically it degrades much less than lithium, but it has much more round-trip, it has much less round-trip efficiency and much more self-discharge. So basically it has much more energy loss, which you can see here as well, that the energy loss portion of it is much higher compared to LFP option. And also even though you need much less of this non-lithium battery, but given their unit price, it still came out to be higher than the lithium with augmentation. So now you can look at maybe another option you could be looking at, if lithium with overbuild, how would that compare against this non-lithium? So there are these different scenarios you can study with the help of the right tools that will help you make a lot more informed decision. In this particular scenario, the lithium with augmentation for this particular 4-hour duration project came out to be the most cost-effective one. And then eventually, very, very important part of the equation is all these calculations are based on a lot of technical parameters. One important one that I would like to mention is the auxiliary load, right? So for lithium, current practice nowadays are very high level, 2%, 3% estimation based on Excel, but that's really is not what you see in practice when the project is operational. It really depends on your enclosure construction, it depends on your ambient temperature, it depends on your use cases. So all these factors impact your auxiliary estimation. So that's where you need more detailed tools that can help you do that. So this is one of the examples from Storlytics, which shows you the monthly distribution of your auxiliaries, and you can see over the summer months and in winter months, it's higher compared to the shoulder months. It's going to vary depending on the location. So if you do a project in Charlotte, North Carolina versus in Arizona, you will see much different profile for your auxiliaries. And you also have much detailed breakdown of your losses. It helps with your auxiliary load estimation, and then it also helps you to make decision about your whether your auxiliaries needs to be sourced from external or internal. Of course, you can source your auxiliaries from a separate freight from transmission and all. That will help to improve your round-trip efficiency, because that's been now not part of your overall battery system. But if you chose it to be part of the battery system, then your round-trip efficiency is going to take a hit, and then there is going to be some estimation impact on the sizing of your battery system. So with that, I think that was my last slide. So Christina, I'll pass it over to you. If there is a Q&A questions, I would like to answer those.
Perfect. Well, thank you so much, Jakir, for that presentation. You do have a couple of questions coming. So I do have a couple of pre-submitted I wanted to start with while we see the flow of the questions get bigger. We will try to reach as many as we can. However, no worries, because we always send to our panelists the questions in case they want to respond by email as well. So Carlos, I'm going to start with you. So first question is, how is the useful life calculated when there are multiple applications of use at the same time?
Okay. As Jakir also explained in the presentation, the useful life of the battery energy storage system directly depends on the cycling of the battery. When operating in countries where the battery can participate in various electricity markets, it's important to calculate the equivalent cycling. For example, a battery typically completes around one cycle when operating only in the day-ahead market. However, if other markets are available, we need to optimize the battery's mode of operation. In our case, in ETS storage, we use an in-house optimization tool to determine the optimal best size and operation mode for participating in different markets. Then we can provide you in the technical specification for the manufacturer the equivalent cycling that it is a crucial parameter to include in the technical specification of the contract and of the request for proposal for the different manufacturers.
Okay, perfect. Well, thank you. Jakir, I see that I was going to ask you if other non-lithium energy storage systems exhibit similar degradation characteristics, but I also see a question from Polo is asking about another type of battery, I think, to use the graphene battery instead of lithium one. Could you give us like a whole overview of this question?
Me do that. Yeah, so first part is the parameters that impact degradation varies from chemistry to chemistry. So the one that I presented to the lithium, for some non-lithium technology, you'll not see that maybe the depth of discharge or average SOC is not as impactful as throughput. So really, that's why you have to model each technology in detail, understand the underlying characteristics, right, that impacts degradation, and do some accurate modeling, because what is true for lithium is not necessarily true for non-lithium. And then to Polo's question, yeah, we have not looked into the graphene battery yet. We have some of those in the pipeline. Sodium ion graphene, those are coming in the pipeline. Yes.
Okay, thank you so much, Jakir. Next question for Carlos. What is your opinion about flexible warranties?
Okay, flexible warranties are an interesting option in case regulation changes in a particular country. In many countries now, best regulations are still being developed and the rules are continually changing. For instance, if a new electricity market becomes available for best operation and we want to participate in it, the battery's mode of operation may change. It's probably going to change. Probably it's going to increase the shares and discharges and increase the cycle per day. In such cases, it will be beneficial to adjust the warranty condition to reflect the updated number of cycles per day. Then we need to contact to the integrator or manufacturer to change some condition of our flexible warranties. Then we consider that it is a very, very interesting option inside the contract, in the negotiation of the contract.
Okay. Perfect. Well, thank you for that. Next question to Jakir. In conclusion, we should always do the comparison scenarios. What recommendations should we keep in mind for each scenario?
Yeah, so really, basically, first thing you have to take away from this is any conclusion you made really needs to be a profile specific. Right, so you need to have a clear understanding how you plan to use this battery, and that forms the basis for your analysis. And then when you are doing this comparison, you also need to understand the project requirements. Is your project, if there are penalties, like if you fall behind fall below your required capacity, and if there are penalties for that, then absolutely you have to plan ahead to make sure you don't fall below the guaranteed limits, right? So that's where you need detailed analysis and study with accurate models to be able to make informed decision. The factors to come, the decision-making factors really varies from scenarios to scenarios and projects to projects. But let's say for an overbuild versus augmentation scenario, which one to go with, right? Your first criteria needs to be both of them should be technically sound, right? So both should meet the technical requirements of the projects. Then your decision making, if both are meeting the technical requirements, then your decision making then becomes looking at the cost side of things, and then look at which choice is more beneficial in terms of cost, and then go with that one. Okay. And of course, with terms of augmentation, there are different augmentation strategies, AC augmentation, DC augmentation, and each one has its own perks. So you have to take those into consideration. Yes.
Okay, perfect. Well, thank you so much for that answer. Of course, and any of you, even though I direct the specific question to someone, if you would like to add something to the response, please let me know. If not, I'll just continue going on. So next question, Carlos, this one's for you. And it's the first one by Carlos Melendez. He says, apart from taking into account the degradation of the batteries, you indicated that we have to be careful with the life of PCS. What is the best strategy to make the batteries last so long in a 30-year project?
Okay, thank you for the question, Carlos. Regarding the system, not only we need to be careful about the PCS, also about the degradation of the cell, because we think that the most important and most critical parameter is the degradation of the battery. One of the best options is to contract, in this case, a performance warranty, because the degradation of their RT, the round trip efficiency from one way for charge and discharge, the RT applies usually at the output of the power station, and the performance warranty is going to include the PCS degradation and the batteries degradation. Here is going only, it's only to be degraded the batteries. There are some manufacturers that warranty up to 20 years. Some of them are now starting to warranty 25 years more, up to 25. But if you would like, in your case, to reach a particular power or energy at the year 30, you will probably need to follow an augmentation strategy or install more energy in the future, and it is depend on the particular project and depend on the particular requirement of your project. Then we can analyze it if you want, and give to you different options to reach a particular power at year 30, for example.
Okay, perfect. Thank you, Carlos. Next question from Tomas to Jakir. Great presentation, by the way. In your opinion, do we need to leave a gap of DOD in the cycling or let them discharge at 100% DOD? Thanks.
Sorry, I was on mute. Yeah, so solely from a chemistry perspective, yes, if you do 100% DOD, then you are putting the most stress on the batteries and they're going to degrade, right? But then the question becomes, if your use case need it depends on if you're not in a market, right? So maybe you're providing a grid service like an upgrade deferral and all, like peak load shaving. So in that scenario, your use case will dictate that how much you will need to discharge your battery. And if the use case needed and that's the purpose of the project, then you will have to you do 100% DOD. But just remember, keep in mind that that's going to cost most degradation. So you will have to oversize your battery, taking that into account. Yeah, yes. So it's not like a reliability issue or anything. It's just a performance that happens because of the chemistry.
Perfect. Well, thank you for that. Next question from Wayne. I think Jakir is from your presentation, because he asked, what is the chemistry of the battery that is classified as non-lithium ion technology in your comparative analysis?
I don't think we can share specific technology name or pricing at this point. Yes. Okay. Sorry about that.
No worries. Perfect. Okay, next question. I don't quite understand additional costs to be included, fire protection system, disposal cost. Carlos, because this one might be for you, talking about the different costs.
Yeah, in general lines and the OPEX, we must include the fire protection system as you mentioned, and also the disposal costs at the end of the life of the project. The OPEX depend on the analysis, but the OPEX must include all the warranties, including the fire protection system, and the operation and maintenance, but it's also depend on the contract you have with the integrator.
Okay. Perfect. Next question is, do you have an idea about OPEX average value? I think this was for you, or well, whoever knows your response can answer it. Do you have an idea about OPEX average value, euros megawatts for Leon batteries, C rate 0.25? Maybe this one's for you, Jakir. I don't know, I'm just guessing.
Yeah, I mean, I don't have the full OPEX, but just the state of health, the performance guarantee, what I have seen ranges between, I would say $1.3 to $1.6 per kWh. That's what my experience has been.
Okay. Perfect. Then we have a question from Pierre Jean Charest. Pierre, we'll put you in contact with both of our speakers so they can give you all the information about what they do. And it's a perfect timing because I think we are all set. Or Jakir, I'm seeing that you're writing. Do you want to
Yeah, I was just
talk
going to
about
reply
it?
to Pierre. Yep.
Perfect. So as we're coming to an end for this webinar, thank you so much, Carlos and Jakir, for this webinar. Great presentations, great questions also from the audience. If you're interested in knowing more about our event happening in Panama, the 29th and 30th of October, please let us know. We have here all the information if you want to get to know about the news, the upcoming webinars that we have, both in Spanish and in English. This is the link. Let me just send it here. And we hope to see everyone very soon in one of our other webinars. So thank you for so much. I hope you have everyone a great day. Thank you. Bye.
Thank you. Thank you. Thank you.
Bye.